Good morning to all. I am Dr. Mohamed Shuaib, Professor in the Department of Electrical and Electronics Engineering, B.S.Abdur Rahman, Crescent, Institute of Science and Technology. Today I am going to discuss about the topic on Introduction to Electric Power Quality, which comes under the course Electric Power Quality for B.Tech EEE students. The course objectives for this Electric Power Quality course are to acquire knowledge on factors affecting power quality, to study the effects of sag and interruptions, to study the cause of harmonics, to study the different types of power filters to eliminate harmonics, and to familiarize the power quality monitoring devices. The syllabus for the module Introduction to Power Quality terms and definitions, short duration variations such as voltage sag, voltage swell, voltage imbalance, voltage fluctuations, interruption, long duration variations such as under voltage, over voltage, sustained interruption, power frequency variations, concepts of transients, international standards of power quality, power acceptability curves, Computer Business Equipment Manufacturers Association curve, and ITI curve, and IEEE and IEC electrical standards. So therefore, power quality. So what is a power quality? Maintaining a sinusoidal waveform of a bus voltage or currents at rated voltage or current and frequency. So that is what we define as power quality. The waveform of electric power quality at generation stage is purely sinusoidal and free from any distortion. However, there are many devices that distort the sinusoidal nature of the waveform. These distortions may propagate all over the electrical network. Causes for power quality deterioration. First are natural causes. Faults or lightning strikes on transmission lines or distribution feeders. Second one, falling of trees or branches on distribution feeders during stormy conditions, equipment failure, etc. Second one, due to non-linear loads, that is equipment or transmission or feeder operation. So here, the transformer energization, a capacitor or feeder switching, power electronic loads, that is UPS, ASDs, converters, etc., and arc furnaces and induction heating systems, switching on of large loads comes under this non-linear loads. Sources of power quality problems. So load equipment and components. Here, the converters, pulse modulated loads, machine drives, arc furnaces, computers, UPS, television sets, fluorescent and other gas discharging lighting, certain components which employ magnetic circuits. Second one, subsystems of the transmission and distribution system, that is grounding systems, resistance systems, etc. Therefore, power quality is ultimately a consumer driven issue which you define the power quality as any power problem manifested in voltage, current or frequency deviations that result in failure or misoperation of customer equipment. So here is the line diagram for a power quality, a power distribution and transmission system. So where you can see the power is generated at one end at the generation site, say hydroelectric dam here, and it transmitted over long transmission lines to the customer location through distribution lines. And we can also say power quality is equal to voltage quality. The utility can only control the quality of the voltage. It has no control over the currents that particular load might draw. Therefore, the standards in the power quality area are devoted to maintaining the supply voltage within certain limits. Load current changed due to variety of disturbances. Generators may provide a near perfect sine wave voltage. The current passing through the impedance of a system can cause a variety of disturbances to the voltage. For example, current resulting from a short circuit causes the voltage to sag or disappear completely. Currents from lightning strokes passing through the power system cause high impulse voltages that frequently flash over insulation and lead to other phenomena such as short circuits. Distorted currents from harmonic producing loads also distort the voltage as they pass through the system impedance. Thus, a distorted voltage is presented to other end users. Increased concern about the quality of electric power. All utility customers. Customers always want to increase productivity. Manufacturer side, they want faster, more productive, more efficient machinery. On the utility side, utilities encourage this effort because it helps their customers become more profitable. Let's see the example for linear loads. They are resistive elements, inductive elements and capacitive elements. These are major groups. In resistive element group, incandescent lighting, electric heaters, falls under this resistive elements group. Inductive elements consists of induction motors, current limiting reactors, induction generators, windmills, damping reactors used to attenuate harmonics, tuning reactors in harmonic filters. In the case of capacitive elements group, power factor correction capacitor banks, underground cables, insulated cables, capacitors used in harmonic filters. Example for nonlinear loads. So these are example nonlinear loads, so which use in our day-to-day life. A digital clock, a personal computer, a cell phone, heart monitors in medical field, all those are examples for nonlinear loads. And also in the case of industries, the adjustable speed drives that control the speed and torque of the motor and the drive, electronic ballast lightning, a mass lightning in a very large semi hall, or arc welding equipment. Typical power quality problems, say a power interruption for a brief period and a voltage sag. The voltage magnitude is less than the rated value. Then voltage swell. The voltage magnitude at a particular instant may be above the rated value, and long duration variations. So the voltage magnitude may vary for a longer duration, and impulsive transients which occurs only for a short duration, and oscillatory transients which occurs over the sinusoidal waveform, and also the harmonic distortion that is due to harmonic loads, and voltage fluctuations and noise. They constitute some of the typical power quality problems. Also the impulse voltage, the sag, distortion, all these are examples for power quality problems. You can see the waveforms here. The impulse voltage occurs only for a momentary period. Similarly for sag occurs again for a shorter duration, and that can be recovered by using suitable methods. Similarly distortion due to harmonics, that also can be eliminated using suitable filters. Classification of power quality according to the source. Converters. The converters, based on converters, the power quality can be classified. Magnetic circuit non-linearity, and arc furnace, or by the wave shape of signal such as harmonics, flicker, or by the frequency spectrum, radio frequency interference. As per IEC, that is International Electrotechnical Commission, it classifies this power quality as into groups. In IEC, they call the power quality as electromagnetic phenomena. Therefore, they classify under the heading electromagnetic phenomena into groups: conducted low frequency phenomena, and radiated low frequency phenomena, conducted high frequency phenomena, radiated high frequency phenomena, electrostatic discharge phenomena, nuclear electromagnetic pulse. These are the major classifications. And these are categories and characteristics of power system electromagnetic phenomena. Say for example, the category transients, and also impulsive transients, oscillatory transients. So you know, these impulsive transients, oscillatory transients are classified based on the instant of occurrence and the time of occurrence. And the impulsive transients is very short, occurs very short duration, and oscillatory transients occurs for a relatively longer duration. And short duration variations, in this you have instantaneous, and you have momentary and temporary. So these are three major classifications within these short duration variations. So here the instantaneous variations occurs for 0.5 to 30 cycles, and this momentary variations occurs for 30 cycles to 3 seconds. Temporary variation occurs from 3 seconds to 1 minute. Then other category, long duration variations. Long duration variations, whatever change that occurs, so for example the voltage for greater than 1 minute, that is classified as long duration variation. Then you have we have voltage imbalance. Voltage imbalance, that is the typical duration is steady state, and the voltage magnitude is typically 0.5 to 2%. Then DC offset, waveform distortion. Again, there is a distortion in the sinusoidal shape of the waveform. Then you have DC offset. In DC offset, the average value of the waveform is not equal to 0, because there may be higher value in the positive side or the negative side. The harmonics. Harmonic nothing but when the sinusoidal nature of the waveform is disturbed because of nonlinear loads, and this classified as harmonics. Interharmonics. Interharmonics are those harmonics which lies in between the two order of harmonics. For example, between first order harmonics and third order, or between second order and fourth order. And notching. Notching is a phenomenon occurs for a very short duration in the periphery of sinusoidal waveform, and where the voltage value decreases for a very short duration across the periphery of the waveform. Then noise. Noise, again, disturbance occurs in the electrical signal. And voltage fluctuations, which means the voltage continuously varies at a lower frequency, shorter frequency. Then power frequency variation. This is also classified as a power quality problem, where the power frequency will not be a steady value. For example, in India, it is 50 Hz is a standard frequency. The frequency may not be 50 Hz, maybe 50.1 Hz or 49.9 Hz or 8 Hz. Then power quality phenomena, types, characteristics and their origin. Here, the transients. It can be classified into two categories: impulsive, oscillatory. Impulsive transient. It is a sudden non-frequency change in the steady state condition of voltage, current or both. It is unidirectional in polarity, primarily either positive or negative. Impulsive transients are normally characterized by their rise and decay times, which can also be revealed by their spectral content. So this is one of the typical impulsive transient, that is current impulsive transient. So you can see the waveform. Oscillatory transient. It is a sudden non-power frequency change in the steady state condition of voltage, current or both. It includes both positive and negative polarity values. It consists of a voltage or current whose instantaneous value changes polarity rapidly. The difference between the oscillatory and the other transient is, in oscillatory it occurs in both positive and negative sides, whereas in the impulsive it is only on one side. Oscillatory transients due to capacitor switching or due to cable switching. You can see due to back-to-back capacitor switching, the impulsive the oscillatory transients are shown in this figure. See how the waveforms are oscillatory, and it is dying out as it progresses on. And oscillatory transient due to capacitor bank energization, you can see in the low frequency oscillatory transients caused by capacitor bank energization for a typical 34.5 kV bus voltage. So the oscillatory transients continues around the sinusoidal periphery of the waveform. So oscillatory transients due to ferroresonance transformer. So you can see how the waveform is being disturbed in a relatively larger manner, larger magnitude. Short duration variations. Each type of variation can be designated as instantaneous, momentary and temporary depending on its duration. We have already seen that. For example, 0.5 to 3 seconds comes an instantaneous, 3 seconds 1 minute momentary, and greater than 1 minute greater than that it is classified as a long duration variation. It causes here fault conditions, the energization of large blocks of loads which require high starting currents, intermittent loose connections in power wiring. Depending on the fault location and system conditions, the fault can cause either temporary voltage drops, that is sags, or voltage swells, that is voltage rise, or a complete loss of voltage interruptions. Interruption. What is the interruption? An interruption occurs when the supply voltage or load current decreases to less than 0.1 pu for a period of not exceeding 1 minute. Causes for interruption: results of power system faults, equipment failure and control system malfunction. Interruption are measured by their duration. Since the voltage magnitude is always less than 10% of nominal, the duration of an interruption due to a fault on the utility system is determined by the operating time of utility protective devices. Instantaneous reclosing generally will limit the interruption caused by a non-permanent fault to less than 30 cycles. Delayed reclosing of the protective device may cause a momentary or temporary interruption. The duration of interruption due to equipment malfunctions or loose connections can be irregular. The figure shows a momentary interruption due to which a voltage on one phase sags to about 20% for about 3 cycles and then drops to 0 for about 1.8 seconds until the recloser closes back in. So you can see here what just now I said. So there is a voltage swell and there is an interruption for about 0.5 cycles. After that, voltage rises and at about 1.25 seconds. So this is how this interruption occurs. Sags. A sag is a decrease in RMS voltage or current between 0.1 to 0.9 pu at rated power frequency for durations from 0.5 cycle to 1 minute. Causes of voltage sags associated with system faults. So whenever the system fault is there, voltage sag will occur. Energization of heavy loads. So when heavy loads are switched on, the voltage sag will occur. Similarly, the starting of large motors. So during starting, the voltage dips. So sag durations are subdivided here into three categories such as instantaneous 0.5 to 3 cycles, momentary 30 cycles to 3 seconds, then temporary 30 cycles 3 seconds, temporary 3 seconds to 1 minute. So you can see the example here, the voltage sag that is caused due to single line ground fault on another feeder from the same substation. You can see the voltage dips from the rated value. It dips as low as 0.65, and again after a few seconds the voltage improves to the rated value. So you can also see the voltage waveform here. So where the voltage magnitude dips from the rated value. So another example where the voltage sag occurs due to large motor starting. Actually, the induction motor draw 6 to 10 times its full load current during starting. So that causes that much voltage drop. As the current value increases during starting, that much voltage drop will occur. So therefore, the voltage sag. That occurs only for a shorter duration. After that, the voltage improves when the speed increases. Swell. A swell is defined as an increase in RMS voltage or current from 1.1 to 1.8 pu at rated power frequency for durations from 0.5 cycle to 1 minute. Swells are characterized by their magnitude and duration. Swell durations are subdivided into three categories, with instantaneous 0.5 to 30 cycles, momentary 30 cycles to 3 seconds, and temporary 3 seconds to 1 minute. This class is same as the sag. Terms of voltage swell. This is associated with the system faults. And second, energization of large capacitor bank. So when a large capacitor bank are energized, then voltage will increase. Similarly, switching off large load. When large load is taken out of the system, then again it causes voltage rise or voltage swell. The severity of voltage swell during a fault condition is a function of fault location, system impedance, and grounding. Voltage swell due to single line to ground fault. You can see here voltage swell. As you saw an example for a voltage sag, similarly the voltage swell during single line to ground fault where the voltage rises above the 1 pu, and after that the voltage restored to normal value. Long duration voltage variations. This long duration voltage variations encompasses RMS deviations at power frequency for longer than 1 minute. It can be over voltage, under voltages, sustained interruptions. Over voltage. Increase in RMS AC voltage greater than 100% at the power frequency for a duration longer than 1 minute. This is called as over voltage. And it causes load switching, that is switching off a large load or energizing a capacitor bank. A second cause, incorrect top settings on transformers can also result in system over voltages. Its effect, the over voltage results because either the system is too weak for the desired voltage regulation or voltage controls are inadequate. Over voltages and under voltages generally are not the result of system faults but are caused by the load variations on the system and system switching operations. And long duration variations are typically displayed as plots of RMS voltage versus time. Under voltage. Decrease in RMS AC voltage to less than 90% at the power frequency for a duration longer than 1 minute. The load switching example, switching on a large load or overloading and due to the faults on the lines. And the causes, a load switching on or a capacitor bank switching off can cause an under voltage until voltage regulation equipment on the system can bring the voltage back to the within tolerances. And second, overloaded circuits can result in under voltages. Sustained interruption. When supply voltage has been zero for a period of time more than 1 minute, the long duration voltage variation is considered a sustained interruption. This term has been defined to more specific regarding the absence of voltage for longer periods. Causes: power system faults, equipment failures, control malfunctions. Voltage imbalance, that is voltage unbalance. So when for a balanced voltage, all the three phases should have the same voltage magnitude. In the case of voltage imbalance, the ratio of, the negative or zero sequence component to the positive sequence component, it is called as a voltage imbalance. Actually, all the three phases will not have the same voltage magnitude. Sources for voltage imbalance. Generally, they result from unbalanced loads, single phase loads on a three-phase circuits less than 2%, results of failure in any one phase of a three-phase capacitor bank. Then severe voltage unbalance, say greater than 5%, can result from single phasing conditions. Voltage unbalance can be calculated like this: maximum deviation from average voltage divided by average voltage multiplied by 100, where average voltage is equal to sum of voltage of each phase divided by 3. Voltage imbalance under unbalanced load condition, you can see here, say the voltage, unbalanced voltage in this waveform. So this is a typical example for a residential feeder. The voltage is not of constant magnitude in the phases. A waveform distortion. It is defined as steady state deviation from an ideal sine wave of power frequency, principally characterized by the spectral content of the deviation. There are 5 types of waveform distortion. 1 is DC offset, 2 harmonics, 3 interharmonics, 4 notching, 5 noise. DC offset. The presence of DC voltage or current in an AC power system is termed as DC offset. And this can be also measured. The average value of a waveform, when it is not equal to 0, then there is a DC offset. Harmonics. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the frequency at which the supply system is designed to operate. IEEE standard 519/1992 provides guidelines for harmonic current and voltage distortion levels on distribution and transmission circuits. Periodically distorted waveforms can be decomposed into a sum of fundamental frequency and the harmonic frequency waveforms. Harmonic distortion originates in the nonlinear characteristics of devices and loads on the power system. Harmonic distortion levels are described by the complete harmonic spectrum with the magnitudes and phase angles of each individual harmonic component. Total harmonic distortion. It is a measure of the effective value of harmonic distortion. Then THD. So this is also called as THD. So THD is used to refer to the voltage distortion in both voltage and current. Used to characterize both current and voltage waves. However, THD refers distortion in voltage wave. So now here, this distortion can be measured from the loads which utilizes ASDs as its input. So these are the typical waveforms for this ASD's input current, adjustable speed as input current. So you can see the sinusoidal waveform is being distorted. In the second waveform, you can see the harmonic spectrum in this type of ASD's connected loads. So you can see the fundamental frequency. Other than that, you have various other frequencies which contributes to the harmonics. And IEEE 509 sets limits on THD for utility side of the meter. Utility is responsible for the voltage distortion at the point of common coupling between the utility and the end user. Total harmonic distortion is a way to evaluate the voltage distortion effects of injecting harmonic currents into the utility system. So how to calculate THD? So THD is given by the ratio of the harmonic currents to the fundamental current. So you can calculate like this: the square root of the squares of the sum of the currents, that is IH, when that is divided by the fundamental current, that is called as a THD. So this example to demonstrate the THD. So in this, apart from fundamentals, you have a third harmonic, fifth, seventh, ninth harmonic values are given. So you find the harmonic voltage, that divided by the fundamental value, that is 114, you will get THD. Here it is calculated as 4.23%. Total demand distortion. Again, the IEEE 519 sets limits for this TDD for the inducer side. So this is with reference to the load current. So this deals with evaluating the current distortions caused by harmonic currents in the inducer facilities. So this can be calculated by the sum of the harmonic currents and its squares with the square root divided by the load current. Here the ratio is divided by the load current. Interharmonics. Voltage harmonics having frequency components that are non-integer multiples of the fundamental frequency. Source of interharmonic waveform distortion, static frequency converters, cyclic converters, induction furnaces, arc devices. So these will contribute to interharmonics. So these interharmonics will not have the integer multiples of this fundamental frequency, but the fraction of the integer values. So this is a notch. A notch is a disturbance caused in the periphery of sinusoidal waveform where the voltage value decreases at few points in the sinusoidal waveform. So notching is a periodic voltage disturbance caused by the normal operation of power electronic devices when the current is commutated from one phase to another. Noise. Noise is defined as unwanted electrical signals with broadband spectral content lower than 200 kHz superimposed upon the power system voltage or current in phase conductors, are found on neutral conductors or on signal lines. Sources. Power electronic devices, control circuits, arcing equipment, loads with solid state rectifiers and switching power supplies are the sources for noise. Voltage fluctuation, that is voltage flicker. Voltage fluctuations are symptomatic variations of voltage envelope or series of random voltage changes, the magnitude of which does not normally exceed the voltage ranges specified by ANSI C84.1 of 0.9 to 1.1 pu. So there will be continuous variations in the voltage magnitude, which differs from 0.9 to 1.1 pu as per ANSI C84.1 standard. The source for voltage flicker, loads that can exhibit continuous rapid variations in the load current magnitude can cause voltage variations that are often referred to as flicker. This is an example for flicker. You can see the waveform where the voltage continuously varies around the sinusoidal periphery. This is an example for arc furnace. Now, power frequency variations. Power frequency variations are defined as the deviation of the power system fundamental frequency from its specified nominal value. So the fundamental frequency, for example, in India it is 50 Hz, some other countries it is 60 Hz. So when the frequency value varies other than 60, either a little bit above or a little bit low, this is again called as power frequency variation. So you can see the this current waveform where you can see the RMS value. You can calculate RMS value. The average value can be calculated, and from average value you can calculate RMS value, right? And this RMS value is equal to 0.707 of the peak value. From this you can calculate P factor, crest factor. This is ratio of peak to RMS value. So for a sinusoidal waveform it is 1.414. CB marker. What is CB marker? Computer Business Equipment Manufacturer Association has come with a curve which says how much your computer can withstand the voltage change. A set of curves representing the withstanding capability of computers in terms of magnitude and duration of the voltage disturbance. You can see the curve. So this CB marker, you can see this curve which is plotted between percentage of voltage and time in cycles, that is for example for 60 Hz frequency. So you can see the voltage the system can withstand the voltage between 87% to 106%. So you can see the voltage variation at various frequency. For example, at 50 cycles or 60 Hz, you can see here. So the voltage variation. So the lower permissible limit is 87%, and upper permissible limit is 106% of the voltage, electrical voltage. Here the points below the envelope are presumed to cause the load to drop out due to lack of energy. Similarly, the points above the envelope are presumed to cause other malfunctions such as insulation failure, over voltage, trip, and over excitation. Then there is another curve which is developed after CBMR curve is ITIC curve. Information Technology Industry Council they have come out with another set of curves, which gives the capable limits of the computers, which is connected to 120 volts power systems in terms of magnitude and duration of the voltage disturbance. So this ITSC curves replace the curves originally developed by ITS predecessor, that is CBMA. So this is again CBMA curve, which again this is applicable for this 120 volts supply system, and it is a curve drawn between this voltage and the time. So you can see at various time, for example 20 milliseconds, after 50 cycles, you can see the voltage limits from here, say from 72. So at 20 cycles, 20 milliseconds, you can see from, that is the lower limit is 70 and the upper limit is 120 volts. So thank you. With this, we come to the end of this module 1, Introduction to Power Quality. Thank you.